cover everything you need to know about Azure Cosmos DB in 45 minutes. I think it's an ambitious goal. I have about 41.6 seconds per slide. Some will take less, some will go a little bit longer, but I found this is something I've wanted to complete, a deck that covers at least most of the things that both the business and technical folks, architects and developers care about when it comes to the when, where, why, and how to use Azure Cosmos DB. Because it's a big and exciting product. So also throughout the presentation, if you could react whenever you see content that you think is AI generated. There's some AI generated content in this deck. So if you could just do a thumbs up or a heart or a laugh, just let me know when you see that that AI content, and we'll see how good OpenAI is doing these days. Just a brief introduction. I'm Steve Flowers. I'm a cloud solution architect focused on data and AI. Been at Microsoft for 4 years, and I'm an Azure Cosmos DB technical insider, which means I work a lot with customers in their Azure Cosmos DB use cases. And I've also authored a study guide for the DP 420 exam, which is the Azure Cosmos DB exam. So it's a great exam to take if you are looking to learn Cosmos DB because it covers all the basics. It's also a good exam to take if you're trying to get your development team prepped for an Azure Cosmos DB use case or deployment to show that everybody's ready to take on that challenge. So Azure Cosmos DB is the platform on the docket for the day, and it is a modern, scalable, serverless, fully managed NoSQL platform, but it's also multimodal. It supports up to 6 APIs today, and I'll cover those APIs here shortly. But the benefits of Azure Cosmos DB range around the fact that it's a modern database platform. So right out of the box, it supports AI-powered experiences. The NoSQL API is a semi-structured NoSQL schema. And most of the primary data sets for things like OpenAI use cases today are documents. So we do that document analysis and we can store that in JSON. But it's also great for developers because it supports multiple APIs, not just NoSQL, but we have a Cassandra API, Mongo, Graph, etc. And we have the SDKs that developers rely on to develop against it, and the features that developers rely on, which we will also cover. It's also mission critical at any scale. I've seen customers using Cosmos DB for small web apps where they only have hundreds or maybe thousands of requests a day, to the most mission critical apps for large organizations. And we'll talk through who some of those organizations are. But the thing to remember is that Cosmos DB can scale from a very small instance to an incredibly large instance instantaneously, while also being backed by industry-leading SLAs, less than 10 millisecond latency for reads and 5 nines of availability. And it's fully managed and cost-effective. Fully managed, you don't have to worry about updates. Your infrastructure team or your DevOps team can build scripts and bicep files or Terraform to deploy the service in the same way while also accommodating the needs of the developers across multiple APIs. So it's a fully managed service. As I mentioned, it's multimodal. We support 6 APIs. The Postgres API, which is a table-based API based on the Postgres Citus project. We can take tables and scale them out across distributed nodes. The table API, which relates to Azure Table Storage, Key Value Store, Cassandra, Column Family Store, NoSQL, our flagship API that's based on documents. So we think about JSON. MongoDB, which is also a document store. We support migrations to MongoDB where developers can bring those MongoDB skills. And then the Gremlin API, which allows you to build graph use cases on top of Cosmos DB. And all these APIs are using the same managed service underneath, but we are presenting the API to the developer to access different functionality based on the needs of the application. So you can see again why that is very critical for infrastructure and DevOps. They can deploy the same service in the same way multiple times across projects. Developers can access APIs to fit the needs for their use case. And Cosmos DB supports performance at any scale, as I mentioned. If you have very small needs, only a couple hundred applications or users using your application versus thousands, tens of thousands, hundreds of thousands of users using your application, Cosmos DB can scale to fit those needs and have the reliability that we're looking for. Again, the 5 nines of availability, less than 10 milliseconds of latency for a read operation against a single document. And we can also reach zero RPO, so zero data loss, right, with that recovery point objective by enabling a strong consistency model. And we'll talk more about consistency here in a little bit. We can also reach zero downtime with an RTO of 0 by enabling in the NoSQL API multi-region write. So we have write instances all over the world. And that allows us to build that resiliency within our application and also serve the needs of our use case. And we support other resiliency mechanisms like continuous backup and point-in-time restore, and the security mechanisms that you expect from a modern database. So the ability to encrypt all of your data, encrypt it using a key that you manage, and authenticate to the platform, whether it be using Entra ID to the control plane or the data plane where your data is actually stored. And as I mentioned, we can scale out. We start with a small number of physical devices or nodes. In this case, we'll refer to them as physical partitions. And as the needs of our data grow, we can just increase, we can just ask for more resources, and Cosmos DB will create the additional nodes for us. Using autoscale, we can have Cosmos DB handle that for us. If our application is using a small amount of resources today, we release a new product and the usage to our website has tripled or quadrupled, then using autoscale, Cosmos DB will scale out to meet that need without any intervention, and it'll happen instantaneously. For more predictable workloads, we have manual throughput provisioning, where we manually tell Cosmos DB how much power we need, how many resources, and in Cosmos DB, those resources are represented by request units. You'll hear them referred to as RUs. It's basically an atomic level of performance where we bundle CPU, memory, and I/O into that unit. So you don't have to think about, oh, well, this is CPU intensive, but it's not very memory intensive. All that's abstracted away, and it scales linearly. So if you have one document that requires 10 RUs to write the document, you'll spend 10 times much if your number of documents that you're writing increases 10 times. So it makes it very easy to predict costs and keep those costs under control. We also offer a serverless option for smaller workloads with variable use requirements, where you pay for exactly what you use. If you use 5 RUs, you pay for 5 RUs. If you use 1,000 RUs, you pay for 1,000 RUs. Great for those development scenarios, proof of concept application, or maybe just a small sidecar service that does very little work and doesn't have the global resiliency requirements as the rest of your application. And finally, we have newer, the vCore model that's associated with the MongoDB API, and that allows us to not just scale out, but scale up, an instance of our database vertically so that we can support more data on that node versus scaling out where we say, hey, we have tons of data, we need to be able to scale out to support that. In the vCore model, you tend to say, I have a lot of data, I don't plan to distribute it. It's never going to get larger than X, and I don't want to have to worry about some of the headaches of the distribution. Well, then we have the vCore model as well. And as I mentioned, Cosmos DB really fits well into the age of AI that we're all currently living in, because the primary data set for AI today is documents. Everybody wants to know what users are discussing, what programs and initiatives are going on within the organization. They have many teams and analysts who are documenting processes and documenting experiences across their applications. And we can use something like Azure AI document intelligence to peel the data out of that document and store it somewhere. Well, that's semi-structured data, right? It's not very tabular. It doesn't look like a SQL table. It's a document with a header and a title and paragraphs of data. And so what do we do with that data? We store that into a NoSQL service. So Azure Cosmos DB is great in that regard. Additionally, we need to implement vector search on top of that data, because the most common pattern in AI right now for at least generative AI is the RAG pattern, retrieval augmented generation, where we go and get some hints about our data and we feed that to OpenAI so it can help the conversation along, and OpenAI can know about our data while it's responding to users. Much more efficient and less expensive than doing something like actually tuning that model. And so Cosmos DB supports these via NoSQL semi-structured documents and via the MongoDB API for vCore, the vector search. Also, Cosmos DB integrates really nicely with Azure AI Search if you choose to use AI Search for your vector search needs. Migration to Cosmos DB is simple. This is great for developers. I was at my previous organization. We had been using MongoDB, using the Mongoose SDK, Node.js. We'd moved to Cosmos DB. We didn't have to change our code. So if you're looking at an on-prem database platform that you want to migrate in the cloud, but you want to, have the advantage of a modern cloud database that can scale and be globally available, such as Azure Cosmos DB. If you're coming from Cassandra, MongoDB, Dynamo, Couchbase, you can leverage your existing tools and libraries and move your data into Cosmos DB with very little code change. And so it's just a really great experience. And then to take advantage of that turnkey scalability and replication. It's a really fast path to modernizing your applications. And Cosmos DB, as I mentioned, supports the most common SDKs. We have a wide array of APIs for developers to leverage. The NoSQL API and the PostgreSQL APIs. They allow for SQL compatible querying. The NoSQL API stores that data in documents, whereas the Postgres API stores that in tables. And we'll talk more about the differences there in a moment. But the important thing is that we have an API that fits your use case as a developer. And then we have the tools, the SDKs. We have the Azure Cosmos DB emulator, so you can emulate the service locally on your development box without having to spin up an instance and spend resources in the cloud. We also have tools like the Cosmos DB Studio. That's a VS Code extension, which allows you to issue queries and look at the metadata about those queries, such as the cost and latency and indexing and all that good stuff. So from a development perspective, very easy to get up and running. Also, from the indexing perspective, out of the box, we index everything in the NoSQL API. So the goal is to write code and start developing that application quickly. Don't have to worry about indexes right off the bat. But as you get through some of the, let's say the MVP, the minimal viable product of your application, you can move on to that indexing and take a look at how that can be tweaked. So let's talk about some use cases within that are applicable to Azure Cosmos DB, because not every use case is applicable. But as I mentioned, AI-powered apps is a great place to start due to the items we've already discussed: flexible schema and integrations with Azure AI services. IoT use cases are great because we can distribute Cosmos DB all over the world. We can create multiple write regions. I can create a write region on the West Coast and the East Coast. I can have my IoT applications writing to those in a low latency manner. Personalized recommendation engines for e-commerce sites as I'm shopping and ordering and interacting with the products on that page, that can all be ingested in Cosmos DB. And using the Cosmos DB analytical store, we can get that data out of there. It's kind of like a read replica that automatically transforms our data from a JSON document to a columnar, a tabular format for us to perform analytics on and store that analytics back into Cosmos DB for recommendations. And order payment processing, mainly because of the the resiliency of Cosmos DB, right? When we talk about 5 nines, global availability, when you have an application that's taking order and processing payment, you need to ensure that that application is available 24/7. In multi-tenant SaaS applications, both fit well into the NoSQL API and the Postgres API. The NoSQL API is great because of the semi-structured schema. I can create fields on my documents that determine the tenant, and it also allows me to scale out in a distributed manner. Postgres is a little bit more specially tuned to multi-tenant applications because I can actually pin data to a physical node within my Postgres deployment, which provides that data residency, which may be required based on a use case. Zero Friction is an application that came out of the gate requiring scalability and reliability. They're metering and billing for heat suppliers. So again, 24/7, has to scale as customers onboard to the service. It has to have reliability and consistency in the data and be cost efficient as well. Mercedes-Benz is a really great IoT use case. They have vehicles all over the world. As we know, vehicles are computers with wheels now, and they're constantly emitting telemetry. And the quicker you can react to that telemetry, the quicker you can gain insights from that data. So being able to write to Cosmos DB instances all over the world in a really low latency fashion has greatly benefited Mercedes-Benz in that case. Also, this is a more recent one. The NBA started using Cosmos DB as well as other Azure services to help enhance their spectators' experience, but as well as their referees' experience. So a lot of spectator data, who's at the game, and the format of the game, things of that nature, that's all flowing into their application. Referees can take video data that's being stored about the game to learn based on the calls that they have made for accuracy and things like that. OpenAI is backed by Cosmos DB, so we all know when we think about scalable applications, OpenAI went from, at least in the public's perception, near obscurity last December to a household name where, you know, my parents are asking me what it is, and they have been for months, right? So using Azure Cosmos DB, OpenAI was able to scale their web application to meet the need of that onboarding. So let's get into some more of the technical stuff. The first third of that conversation is really focused on business decision makers and those who are hunting for use cases or have a use case they're trying to determine if Cosmos DB is a fit. But from here on out, we're going to talk to the technical crowd a little bit more. And so why are organizations choosing NoSQL over traditional relational stores? If we look at this top graphic, we think about a traditional relational database system, and we think of tables, and we think of all the great stuff that comes with those. ACID compliance, they're very simple to maintain and operate and develop against. There's normalization, and all that is great. But what is that lacking? It's lacking the flexibility. It's lacking the performance. A lot of these ideas were implemented when relational databases first became the norm because storage was really expensive and network connection latency was incredibly slow. So we didn't have all this these extra resources to play around with how we were storing data. But over the last 10, 15 years, as storage continued to drop, as speeds continue to increase in networking, it was determined like, hey, we can actually, we can store this data in a more simple format and provide flexibility, provide scalability, because we can scale out now. Now we can have nodes communicating to each other via fiber, and that latency is so low that your end user won't notice. And then we can reach that performance because one of the problems from a performance perspective that traditional SQL workloads suffer is that it's a very rigid design. And we apply all this normalization on top of that data. Well, that normalization actually costs us performance. We don't think about that, but if I have restrictions or constraints on a table, those constraints have to be applied, which means that data has to be evaluated, right? So we have more flexibility in a NoSQL interface. But it comes with the responsibility of understanding, why are we here in the first place? Why are we choosing NoSQL? It can be daunting at first to make the switch because it feels more complex, but really you have more options and you have more freedom. So we think of relational SQL as data on data on write. We're writing the data. And I'm sorry, the schema on write. We're writing the data, and the schema is being defined by the database. Whereas NoSQL is schema on read. The developer is determining the schema of that data. So if we look at a standard table design, this is the AdventureWorks data out of Azure SQL. This is very typical, right? We have a many-to-many relationship here. It's all very atomic, and we have our keys, and there's there's no duplication of data. And what we decided when we started looking at NoSQL is, hey, duplication of data is not that big of a deal as long as we enact some mechanisms to deal with it. In fact, duplication of data can be good because now we can get that data more quickly, and we can have processes running in the background that deals with that duplication and keeps things in sync. But when you think about something like a massive e-commerce website, they can't afford the latency that comes with some of these normalized mechanisms. And when we look at this and we say, all right, we might want to convert this to NoSQL, how would we do it? Our first step is going to be, hey, can we convert these tables into containers? And then a row will just be a document in NoSQL design. Well, I'm here to tell you that's not what we want to do. So we're going to crumple that up and throw it away. And we're going to think outside of the relational box here and think about what our data needs. So if I have an e-commerce site and perhaps I'm focused on the user's cart where they have items that they plan to purchase. Well, what does that cart needs? It needs a total. They need to know exactly how much they're going to pay. They need to know if there's a discount that's been applied or what the tax is going to be and the products that are there. Well, in the NoSQL world, we want to design our data based on the access pattern of application. So what does that cart need to access? Well, it doesn't need to access all the data about the product. The user probably only cares about the name, the price, and maybe you need the weight to calculate shipping when you check out, and a thumbnail photo, an image of the product. If the user wants more detail about that product, then they can click a link, in which case you would go over to this on the left here, this product container document, well, where it has all the data about the product. And there you can give them an experience of really understanding that product. But in their cart, they just want to see a summary. And so we have a duplication of data here, right? We have data in our product container, such as price and weight, which is also present in the document in our sales container, and we can deal with that. And by dealing with that, we're giving our e-commerce cart a lot of speed. We don't have to deal with all that extra data. We get exactly what the user needs. We can write to this document on the right much more quickly. We can read from that document much more quickly. And from the product container for that product data, not all of it's needed very often. A lot of that's probably back-end data that we use to just organize and categorize our products. So we can break that out. We create a little bit of duplication. We create a reference here between product ID. So we have the actual document that describes the product, and then we have a key to that document within our products array in this JSON document. And as you can see, this provides us with a lot of flexibility. We can build this to fit the needs of our application. So what if we want our relational model with massive global scalability? So we talked about the NoSQL API just now, converting a relational model to NoSQL, but what if we want to keep that relational model? Well, that's where the PostgreSQL API comes in. It is a traditional SQL engine, but it has distributed scale out, courtesy of the Postgres Citus engine. And what we can do is we can create distributed tables across our nodes so that data can continue to scale out. As I mentioned, it's great for multi-tenant applications because we could pin data to a specific node if we have data residency requirements. And we can co-locate data. So if we have a multi-tenant where I have some sort of ID, I could say, keep all this tenant's data co-located so that I don't have to go searching multiple nodes to get a specific tenant's data. And that can be globally distributed. We can create read replicas all over the globe. We can still only have one primary write replica, but we can put read replicas closer to our users so that that read access is much faster and lower latency. So let's take a look at graph next. So organizations are choosing Cosmos DB graph, and a good graph use case that I like to bring up is 6 degrees of Kevin Bacon. A lot of people think about their data, and right away in their mind it feels like a graph because you think about a piece of data and it's interconnected with another piece of data. But that's really not what defines a good graph. A good graph is saying how is Tom Hanks related to Kevin Bacon as far as their career of being actors. I don't know how to get from Tom Hanks to Kevin Bacon without crawling through those relationships, right? So if I don't know what those interconnected relationships are, then a graph database becomes really useful for me. Obviously, this is a simple example, but as you can see here, there is no direct relation between Tom Hanks and Kevin Bacon, but Tom Hanks was in You Got Mail with Meg Ryan, and she was in Top Gun with Tom Cruise. And finally, we arrive at Kevin Bacon. And if we look at what a graph would look like, again, our data looks like this in our head a lot of the times, and when we map it out into relational diagrams. But the trick is that in each one of our vertex, vertex is like our node, so our actual object. So in this case, it is an actor. We also have nodes that are movies, and then we have edges, which are the relationships between those objects. So we could have many different paths to go out here. But this, using the Graph API and using the Gremlin graph query language, we can determine how do we get to Kevin Bacon using all these connections. And we can assume that off these connections, there are more connections and more connections and connections that relate back to these connections. And you could have multiple paths to Kevin Bacon, right? But in this case, we can use the Gremlin API to find the shortest path to Kevin Bacon, which is what we've produced here. So when you think about graph, you want to think about how can I understand the relationship between my entities without knowing what that looks like in advance. You also think about metering. Whether it be water or electrical or gas metering, how do those resources get from point A to point B? What's the shortest path? I have nodes in between, and we can define that relationship using a graph, and then we can query and traverse that graph using Cosmos DB. So I want to go through a brief kind of under the hood on the NoSQL API. Again, that's our flagship, and I think it's from a feature perspective the most capable, and from a scalability and availability perspective the most capable as well. So we have an Azure Cosmos DB account. This is a hierarchy. And we have databases within that account, and then we have containers within the database. The containers are where the data is stored, and the containers define how our data is stored as well. So a database can have many containers, and database can also have many physical partitions underneath, which are providing the resources. We can also take that Cosmos DB account and we can deploy it, an instance of it, into additional regions. So as our requirements change, we can add regions around the globe so that that data is being replicated for us. Again, we don't have to manage that, but we do have a little bit of say in how that gets done. And underneath these instances of our database, we have physical partitions. Kind of looks like a server here because it is the closest thing we can think of to a physical node. And within those physical partitions, we have logical partitions. And those logical partitions are the way that we are sharding our data within those physical partitions. But let me back up one here real quick. I mentioned RUs earlier. So RUs in the NoSQL API define how many resources are given to that account, or a database or a container is where you can apply those RUs. And they get divided evenly amongst the physical partitions. So in this case, I have 30,000 RUs. So each of my 5 partitions will have 6,000 RUs. So you'll start to see why the distributed nature of Cosmos DB is important and why correct partitioning of that data is important. Because in any distributed system, we want to have all of the nodes within our cluster responding to requests. We don't want one node that's overworked, that's called data skew, that node will be overworked and will shut down and return server errors to the client because it can't keep up. Meanwhile, the other nodes that we have out there are sitting idle, not doing anything, and that's wasted efficiency. So the way that we divide up our data is using a partition key, a hash of the partition key value. And based on that hash, a range of hashes will be stored on each physical partition. Again, just think of physical partitions as nodes and the logical partitions of shards within that node. And that's important because logical partition is limited to a single node. So we can't span partitions across multiple physical node boundaries. So we may have larger partitions which take up a majority of a specific node, and we may have nodes with many smaller logical partitions as well. But the goal is to have as much cardinality within our partition key as we can. And when it comes to how many RUs you need, we have a lot of ways for determining that. There are tools for putting in your request, your access patterns, and returning the amount of RUs you would need. You also need 1 RU per gigabyte of data stored. And there is a 20 gigabit max storage per logical partition. Again, because those logical partitions are pinned to a specific node. We also support multi-region, as I've mentioned, but we have multi-region where I have a primary read region, and then I have additional read replicas where I can deploy those close to my users. That's really great if I have a really heavy read workload where reads are happening all over the place, but perhaps writes are much less of a concern. And consistency is desired, so I can have strong consistency between these because I only have one place where I'm writing data. Whereas if I look at a multi-write scenario, by the way, the multi-region with only a single write is our best RPO mechanism. We can have an RPO of 0 there with strong consistency. Whereas in the multi-write configuration, I can have multiple write instances all over the globe. But as you can imagine, we can't have strong consistency, and we'll talk about that in the next slide. But what we do get is write flexibility. So I can guarantee that I'll have an RTO of 0 when it comes to my write availability, that clients will always be able to write. And I want clients to be able to write, and then we'll deal with consistency later. So we have multi-write and we have multi-region where we have a primary write instance. And here's a slide that's just demonstrating the RPO and RTO of these options. As we see, single write with strong consistency has an RPO of 0, and multi-write, which does not support strong consistency, has an RTO of 0. An RTO and RPO of 0 aren't possible. And we'll talk more about this in a moment. But from a regional perspective as well, we have high availability built in with availability zones in Cosmos DB. So we have availability zones to help if there's something that happens within the data center, and then we can deploy multiple regions, whether that is to get the data closer to the users or provide that additional resiliency if something happened to a specific region that our data is still available. So yeah, data is everywhere, and it sounds really easy, but it's not. And distributed data is difficult. But I think Cosmos DB does the best job in the industry of making this approachable for users. Because I don't care if it's Cosmos DB or any product trying to store data in multiple locations and letting people write to multiple locations. This is a very hard problem. But Cosmos DB does a lot to make this easier. But first, let's talk about why this is a problem. So the Pack-Elk theorem, which is based on CAP, it's an expanded version of it, basically just says, in the case of network partitioning, you have to choose between availability and consistency, or else you must choose between latency and consistency. So if we take these two ATMs and they have a network connection and they are transmitting data between them, that's fine, but you have to choose between latency and consistency. For instance, I put a $20 bill into this ATM. Do we want somebody else to be able to put a $20 bill into this ATM right away, or perhaps take out a $20 bill, I should say, right away? Or do we want to wait for the ATM to say, yep, I just got another $20. Let me tell this ATM I have $20. Obviously, we know this is not how it works, but just for this exercise, you would see how consistency is important for an ATM, because perhaps I had $0 before I put in that $20. So in this case, we're choosing consistency. If we chose latency, it would say, yeah, put in the 20 here, let him take out 20. Maybe his account will be negative 20 for 100 milliseconds until this catches up. But that's late. That's the lowering latency, but also lowering consistency perspective. And the other side of it says, well, what if there is a network partition and these can no longer communicate? We have to choose between availability and consistency. If I'm over here trying to put in a $20 bill, and again over here I'm trying to take out a $20 bill, they can't talk anymore. So this one can never know I inserted that $20 bill until this network connection comes back up. So you have two options. Either you shut one of these down so that people can no longer withdraw from it because you can't guarantee the consistency anymore, or you give up consistency and say, hey, even though they can't talk, we'll let this gentleman take his $20 bill out and we'll settle that up later. That's availability, saying that both users can use the ATM, the data may be inconsistent, or hey, we have a network connection issue, we need to shut one of these down, and then when the network connection comes back up, we will make the data consistent again. I think it's really important as we talk about multi-region distributed data. And so Cosmos DB provides the most comprehensive consistency models in the industry. A lot of the competitors provide two, maybe three of these, but I really love, and I've gotten a lot of great feedback from developers who use Cosmos DB on the flexibility of these. So I'll start with strong consistency. Which is on the left. We think about our ATM, like we always want the data to be the same between ATMs. We never want an ATM to have a different number than the other ATM. That's strong consistency. If I put in that $20 bill, before the machine even tells me it accepted my deposit, it's going to go talk to the other machine and say, I just got $20 bills, a $20 bill. Once they both agree that that happened, then it'll come back to me and say, yeah, I accept your $20 bill. If they weren't able to agree on that, it would spit it out and say, nope, I'm sorry, I can't do this. That's strong consistency. It's very similar to what we think about as in an ACID transaction within a SQL database, but it's at the most atomic level, right? It's just this one this one data point. Bounded staleness allows us to get a little bit more flexible with our consistency to say, hey, I'm okay with a certain amount of staleness. Perhaps if that $20 bill, maybe I'll let that person take out that 20, knowing that within the next 20 milliseconds, that's going to be consistent, and the chance of somebody taking that out at the very same time and going negative in their account is very low. So perhaps I'll set bounded staleness of 20 milliseconds. Or if I'm looking at IoT data, there's so much data about temperature coming in. Perhaps we care about temperature in 5-minute windows. Well, if that data is inconsistent up to, let's say, 30 seconds or 100 data points, then that's okay, because we're looking at the average over 5 minutes, and not much is going to change there. Session is great for any user-facing web applications, because I can say within a user session, give them a near strong consistency, meaning that it'll honor all the guarantees of strong. I can read my own writes, and I won't have any dirty reads, dirty writes, things of that nature. I can get nearly strong consistency within my session, and then everybody outside of my session gets eventual consistency. So when you think about an e-commerce site, it's usually what I'm doing is what's pertaining to me. I'm not really concerned with what else is going on in the system. But yeah, that's the session. We're building that consistency around a user specific session. Consistent prefix and eventual consistency are basically the same thing. Eventual just means whenever it arrives, whatever order it arrives in, just let it come as quick as it can. Consistent prefix says, yeah, we want it to arrive as quickly as it can, but we want it to be in order, right? So, and I put ATM and social media on both sides of this to make you aware, like, yeah, ATM, we care about how much money is in my bank account. Social media, my mom went to Outback and uploaded a picture of her blooming onion to Facebook. It doesn't matter if I get that right away, right? But it does matter that she's able to, using her phone, click send, and she sees it's posted and everything looks fine to her. If I don't see it for 30 seconds to a minute or 5 minutes or really ever, it's not going to bother her. Well, it might at Christmas when she asked me about not commenting on our social media enough. But so social media, we don't care as much. We want a good user experience. We want that data to be flowing quickly. And so when we were starting to talk about the way that we're accessing our data, right, and consistency is a big part of that, but the way that we're modeling our data is also very important. So we have three really key ways to model that data. We can embed that data where all the data goes inside a single JSON document. It's really great for contained relationships, one to few, infrequent change. That makes writes more expensive, but reads less expensive. Reference, where I break out my data. So if you think about a list of products, I could store them all in one document, or I can break them out into many documents. That's a reference. I'm going to have many documents. They may share some sort of category, but they'll all be unique. I can update those documents really quickly because they're small. I don't have to read a large document to update one small line on that. I can just update the smaller document. Or hybrid approach, which is what we looked at with my example with the e-commerce cart, where there were products being listed there, but not all the information about those products. That's the hybrid approach. So we see, in embed, I could have 100 products in this document, and the more products I have, the more expensive it's going to be to write that document, and it will be more expensive to read that document if I only want a small subset of that data. When I use reference, I can break those documents out. Now this becomes less expensive to write because I'm not having to read all the user data that I don't care about. I'm just reading about Steve's cart. And again, I guess these are actually kind of the same thing, huh? So the hybrid approach, we have that reference to some of the product information, but not all that product information. And lastly, I want to go through some of the key features in Cosmos DB that developers really love. Talked a little about indexing out of the box. The NoSQL API, the core API indexes everything. But we also support more advanced indexes like spatial indexes, where we can use geospatial data for analysis, such as points, lines, and polygons, and queries that use like distance and within and intersects and things of that nature. And then we have composite indexes for queries which use multiple predicates. So if I want to say where some number is greater than 90 ordered by some number, composite indexes can be built to match that query, greatly increasing the speed and reducing the cost. We talked about partitioning. You may think, like, if you're thinking about some sort of data model you have in your head, you may be saying, well, that sounds difficult to model. I don't know how I would partition that. We also support hierarchical partitioning keys now, where you can have multiple levels. JSON is obviously hierarchical, so I can look at that as I would just like a file system almost. And so by using a single partitioning key, we have to pick a very specific field. But with hierarchical partitioning keys, we can pick a hierarchy of fields, such as region and site, which will break those down into independent logical partitions. We were able to do this before using a synthetic key, where we would concatenate the region and the site, but it made it difficult to update. If the site name were to change, then that partitioning key cannot change without rewriting that document. And also, it's just very difficult for developers to have to think about these things. So with the hierarchical partitioning key, you interact with the object in any other way. You don't have to think about any special considerations. The change feed is a really great feature. Think of it as kind of a pub sub dedicated to your NoSQL documents. As data is coming in and being added or updated, you're getting that information into a change feed. We also now have in preview all versions in deletes mode, which is very similar to SQL's change data capture. The current version of change feed, you get all inserts. And when it comes to updates, you get the current version of the document, but you don't get intermediary updates. If somebody altered that document 10 times before you pulled the change feed, then you won't get those 10 updates. All versions in deletes mode now is in gated preview, and it allows you to see everything with LSN numbers and the whole shebang, just like we would expect in SQL. Azure Cosmos DB comes with an integrated cache. If you've used Redis cache and you need that speed and efficiency at the edge with your clients accessing commonly accessed data and increasing the speed of that, think of Azure Cosmos DB integrated cache as a very low touch in-memory cache for your data. It does read through and write through and all the great stuff you would expect a cache to do, automatic flushing, and you can configure the cache size. The Cosmos DB Analytical Store, I mentioned this briefly earlier, but it's basically a back-end process that converts your JSON NoSQL data into a tabular format. It's basically a read replica of your data in a tabular format. It doesn't spend your RUs. You pay for the storage and some compute, but it doesn't touch your operationalized workload. And using this analytical store, you can connect to it via Databricks or Synapse Spark or Fabric, and you can pull that data in, manipulate that data, provide analytics in a near real-time fashion. You can also transform that data and ingest it back into Cosmos DB. So that you can create, materialized views or transform that data for your needs on the fly. I'd mentioned Cosmos DB Vector Search. It's a similarity search. It's very similar to Azure AI Search, but the fact that it's in Cosmos DB with the MongoDB vCore option means our vector can scale incredibly large compared to something like Azure AI Search. So if we're creating a vector search database based on just an absolute ocean of data, we can support that. Burst capacity, it's also in generally available now. Basically, we collect unused RUs second by second, and that builds up. And within a 5-minute window, if you experience some sort of burst in your throughput, then we'll just use those stored up RUs so that you don't have to scale, or that you don't get rate limited, right? Because if you get rate limited, if you're using more resources than you have provision, then the client will receive an error. But with burst capacity, we can accept some of those spikes that you may not have been predicting. Cosmos DB partition merge. When we scale out Cosmos DB, I mentioned earlier, we get a lot of physical nodes in the background. Well, sometimes I've seen customers scale up really large to support ingesting a ton of data, and then they want to scale back down. Previously, you couldn't do that. You would have to migrate that data. But now we support partition merge, where we can take those partitions and merge them back into fewer physical nodes, greatly reducing your costs. We currently also have priority-based execution in Cosmos DB. The default is high, but essentially using the SDK, you can give an execution priority of low or high. So if you have critical applications, you can set that property to high. Anyone else who's set to low will be deprioritized if there's contention on the system. That's great for noisy databases where perhaps there's some applications that just need to be able to complete their transactions no matter what, and other transactions that can wait. They can wait 30 seconds or 40 milliseconds, things of that nature. And then finally, we have Cosmos DB per partition autoscale. This is in preview, where we're going to allow you to scale specific partitions in specific regions. So one of the biggest complaints we've had is that, hey, I have a secondary read region, but I don't use it for read. It's just there in case a disaster happens. Well, now you'll be able to scale down the RUs that are required, because right now scaling out requires a n plus n, right? The number of nodes, or I'm sorry, instances of your database you have out there. So if you spin up one in East US and then West US, your costs have doubled, and each time you spin up additional instance, those costs continue to increase. So using per partition, per region autoscale, we can say your read replica on the West Coast that you never use, we can scale that down. We can scale up to East US without having to spend that additional cost. And that's it. I think we did okay on time. We still have 8 minutes left. I do have this presentation feedback form, if you don't mind. This is my first time delivering this presentation, and I think we did okay. I did catch a few things we left off there, but I'm covered by the asterisks on the first slide that I was only going to talk about almost everything. But if you could use this form to put in some notes on things you would have liked to see, or maybe things that that are troubling you or that you don't understand that would be good additions to this, please let me know. And at this time, if there are any questions, I'd be glad to take them.
Any questions for Steve before we call day here? Seeing no questions, again, I'd like to highlight the next sessions that we have scheduled. Look for those invites to be sent out shortly. I'll post the next one, the registration for the next one that we have in the QA window. If you'd like to get registered or pass that information along to anybody in your organization, we'd greatly appreciate it. If no one has any last minute questions, I want to thank you for attending and hope to see you at our next sessions. Thanks, everyone.